Okay. So if you're watching the recording, sorry, you just missed a bubble sort. But there are other videos available that cover it if you really need to see it. The answer to the question about bubble sort being often used in mostly sorted lists is, to be honest, I don't think I've ever actually seen bubble sort used for reals other than just when you're teaching people about sorting. So there's better and algorithms that are just as simple. So, all right, let's talk about big O of bubble sort. I'm going to observe that, well, okay, so how many passes through the array did we need? Or will we need in general?
It'll be kind of like a factorial, except we're adding, so n plus n minus 1 plus n minus 2
Oh, I see what you're
times.
saying. Yeah, okay, right. I think you answered the wrong question, though. You got the right answer, but the wrong question. So my question was, how many times do we have to go through through the array? I kind of see what you're getting at, but at this point, I'm not concerned with how many elements in the array we had to look at for each pass. I'm just saying how many of these passes were there, regardless of whether we had to go through all of the items or whether we had to go through, 3 of them. And so the answer to that question is about n, right? That makes sense to everyone?
Yep.
Like if there were 1,000 elements in this array, I'm not talking about comparisons yet. No, I'm talking about how many times we had to go through the entire array.
Right. Sorry. I guess
Okay.
I was saying that in response to Kaylin's
Oh, okay. All right.
post.
So my idea is that I'm sort of gradually explaining how we get to the result. So that's where I'm going with this. So the answer to my question, how many passes, is actually it's n minus 1, right? But we're going to just call that n. So the next question is, how many operations were required each pass through the array? And that gets a little tricky in terms of what it is you're counting exactly. With bubble sort, we could, let's see, comparisons. Yeah, we could count comparisons, and that would make sense. It's interesting with bubble sort because really the part about bubble sort that's taking up a lot of the time is actually having to swap things. I guess we could also say, worst case scenario, how many swaps we're going to have to do each time through the list, right? So whether we count comparisons or swaps doesn't really matter. Basically, we're going to be looking at approximately n items each time, right? The first time through, we look at n items. Just to keep things simple, we could think of it as each pass through the array, we're looking at n items. So we're going to be doing n operations of some sort. Okay? Does that make sense? I know I'm waving my hands a little bit there because deciding what to count is a little tricky. But I hope you get the idea that whatever we count, it's going to basically end up being roughly n, or to be more precise, roughly n divided by 2. But we don't care about the divided by 2, right? So we have n passes approximately. Each pass requires approximately n operations. So the end result is that this is an big O n squared. sort. Anybody want to ask a question about that? Let me try to articulate that again. I'm kind of hoping. And the other thing that I like, so one of the reasons I like actually going through this process is that you end up with a picture here. And you can kind of tell just by the picture that this is going to be big O n squared, right? Because you've got 12 numbers to start with, and you end up with approximately 12 by 12 times 12 numbers on the page. So n squared. All right. If there are no other questions, I'm going to bring up some code here. I don't think I showed you this file last time, did I? Sorry, trying to move my Zoom windows around a little bit. Did I show you this code last time?
All right. Do you intend for us to see something? We
Oh,
don't.
sorry. Thank you.
All good.
Let's try this. Better?
Yep, all good.
Okay,
It's a
so
little bit cut off on the right.
yeah, I think I got it so that the file is cut off, but you can actually see the code, right?
Yeah.
Just because I'm trying to save real estate here on my screen. So, I mean, I guess I could, oh, actually, the window is not really cut off. I'm showing almost all of it. There, now I'm showing all of it.
Yeah.
Okay, so we have, so let me ask my question again. I cannot remember if I showed you this last time.
No, we didn't get that. Well, we saw. You did some code for us, but we didn't see the bubble
Right.
sort code.
Right. Okay. I think I just like did the code for selection sort actually right in the Excel spreadsheet. But okay, so this is just kind of a program that I think is pretty cool. It's basically got 6 different sorting algorithms in it. If you count bubble sort as being one algorithm, I actually have 2 versions of it. And I've got code in here that I can use to actually time them. So and you can see up here that I have set the number of items in the array as 50,000. I can also set this up so it has, like, 20 items, so I can actually test it to see whether it's sorting correctly or not. But typically, just for fun, I like to make this big and see how long it takes. So here's main. Main just makes another copy of the same list, calls, and then times the algorithm. So here's bubble sort. Pretty simple code, right? We're just saying, here's the outer for loop, which is going to go num items minus 1 times. That's when we talked about the fact that there's going to be n minus 1 passes through the array. So each time we execute the body of that for loop, we are doing 1 pass through the array. And so 1 pass through the array is we always start with the index of 0 and we go up to, and this is just an expression that calculates how many items in the array have been still remain to be sorted, right? So we go through all of the items that have not yet been sorted and we swap them if they're in the wrong order. Okay? Any questions about that code? I don't necessarily need you to, like, understand it in excruciating detail, but you should be able to get the main idea. And then here's another version of bubble sort where we check to see whether whether there were any swaps, right? So every time through the array, I'm going to set this variable, this Boolean variable, to false. And then inside the if statement, if I do a swap, I'm going to set did swap to true. Okay, and then I just, every time through the loop, I have to check this Boolean variable, did swap, to see if it is true or not. Okay, and then here's selection sort that we talked about last time. All right, so I think I want to actually try this out. Any guesses how long it's going to take to sort 50,000 items? Let's see, I think I need to save this to the right location. Okay, here we go. We're doing bubble sort 1 right now. And we're waiting to see how long it takes to sort 50,000 items. Oh, there we go, about 9 seconds, right? Now we're waiting on the second bubble sort algorithm. 9.2 seconds. And I must have commented out selection sort. Oops. All right, so anyway, interesting. Let me ask you this. If I were to double the size of the array, so this is sort of a math question. If I were to double the size of the array, what would happen to the amount of time the algorithm would take? Double it, not square it. So, right, I don't know why I said double it, not square it. That made no sense. Right, so if I double the number of items in the array, that means I'm going to multiply the time by 4, right? Because it's a quadratic function. If I double anything in the quadratic function, that means I'm putting a 2 in it. When I square that, I get 4. So if I were to try it with 100,000 items, this would take 40 seconds. Don't worry, I won't do that to you. But you know what we could do, just for fun. I don't know if you guys think this is as fun as I do, but let me put selection sort back in here. And I'm going to make the size 25,000. Right? So if our mathematics is correct, if I divide the size of the array by 2, what's going to happen to the time? Divide by 4, right? So that would mean we would expect this to be about 2¼ seconds, right? So let's try that out. Oops, I'm having a little technical issues here. I wish the Zoom would allow me to just share like all of my desktop except the right, I don't know, 2 inches or something, and then I could put all the Zoom windows over there. 2.2, 2.2. And then selection sort comes in at a rip-roaring 0.7 seconds, right? So I have to say about selection sort, this is weird that it comes in so fast. It really shouldn't be that fast, but it always comes in that fast. When I do this in Visual Studio, it's even faster. It's like almost as fast as Quicksort. So, and you know, I've been trying to figure out why that is for years, and I've talked to all the smart people I know. The best guess that we've been able to come up with is there's some sort of a optimization that's going on when we do a selection sort. I don't know, the compiler recognizes that it's a sorting algorithm and it makes it faster somehow. I don't know, maybe it changes it to a quick sort. I don't know. But anyway, so you just kind of have to take this selection sort time with a grain of salt. That's an interesting idea, Kaylin. Your assignment is to try that out and see what you come up with. Okay, I think we're done talking about bubble sort. So let's go back and move on. Let's talk about insertion sort. Okay, and so I haven't said much about like the names of these algorithms. I hope it sort of makes sense, right? The reason that selection sort is called selection sort is because what we're doing is we are selecting the smallest item in the array and swapping it to the front, right? Bubble sort is called bubble sort because the action of going through the array and swapping items sort of reminded somebody of bubbles bubbling up in liquid, right? Insertion sort is called insertion sort because what we're going to do is we're going to take one item at a time from this list and we're going to insert it into a new list in the correct position, right? So we're going to take the 82, insert it into a new list. I should use the word array. We're going to take the number 82, insert it into a new array. We're going to take, now I'm second guessing myself, maybe the list was just fine. We're going to take the number 55 and we're going to insert that into the new list into the correct position. We're going to take the 92, we're going to insert that into the new list into the correct position. Tricky, one of the things that makes it a little bit tricky is that we're not actually going to have a separate array though. We're just going to form that new list right here in this array in place. So the first step is I'm just going to say, okay, the 82 by itself is already a sorted list with one item in it. Actually, insertion between these three, insertion turns out to be the quickest. Not always, of course, but in general, you know, if I were to try it with, you know, 10,000 different random sets of numbers, it would probably come out fastest. I have no idea what percentage, but 90-something%, I'm pretty sure. And I think you'll see that as we go. It turns out to be pretty cool. Okay, so that's our first step. Our second step is we're going to take the 55 and we're going to insert it. We're going to make it part of the list. So now the list contains two items, the new list. And we're going to make sure we insert it in the correct position, which in this case means we're going to swap the 55 and the 82. Let me just make an observation about this. Unlike the other sorts, this one is actually, the first few passes, I think are more confusing because the list is so small. I think you start to get a real feel for how insertion sort works once we get up to maybe the fourth pass or something like that. So bear with me if this seems a little weird at first. Okay, this will be our second pass, and we're going to be inserting the number 92. And so we compare the 92 with the 82. We see that the 92 is bigger than the 82, which means it's already in the correct position in the new list. So we're done with that. Again, so trivial that it's kind of hard to get a feel for what's going on here. But I think this next pass will be a little more interesting. Okay, so now we're going to be inserting the 67 into the list, but we need to get it into the correct position. So what we do is we compare it to the item to its left, compare it with the item to its left. If it's in the wrong order, we swap them. Okay, keep going. Compare the 67 to the 82. If it's in the wrong position, swap them. Compare the 67 to the 55. Now they're in the correct position, so I know that 67 has been inserted correctly. Everyone okay so far? So basically the idea is every time we are inserting a new number, we're going to put it at the end of the list, and then we're going to swap it down the list until it gets into the correct position. Okay, so now we are adding 90 to the list. Compare the 90 to the 92. It's smaller, so we need to swap them. Yeah. Now compare the 90 to the 82. The 90 is bigger than 82, so that tells us that we're done, and 90 has been inserted into the correct position. All right, we're going to get some more interesting ones here in a minute. Now we are inserting the 38 into the list. So I compare 38 and 92. Need to swap those. Compare the 38 and the 90, need to swap those. Compare the 38 and the 82, need to swap those. Compare the 38 and the 67, need to swap those. Compare the 38 and the 55, need to swap those. Okay, and on this case, notice that normally what happens is we keep swapping until we get to a number that is smaller than the number we are inserting. In this particular case, we didn't stop because we got to a number that was smaller than the number we're inserting. We stopped because we got to index 0 of the array. Okay, let's keep going. So now we are inserting the 15 into the array. And you can see that we're going to just be swapping all the way down, right? So I'm not going to do that in excruciating detail. I'm just going to swap 92 and 15, swap 90 and 15, swap 82 and 15, swap 67 and 15, swap 55 and 15, swap 38 and 15. Okay. We got 5 more to go, 5 more numbers to insert. So now we're inserting the 53 into the new list. 53 and 92 swap. 53 and 90 swap. 53 and 82 swap. 53 and 67 swap. 53 and 55 swap. 53 and 38 don't swap. I'm done. I guess I should just do this with, I don't know, 8 numbers instead of 12 or something like that. All right, now we're inserting the number 96. Compare 96 to 92, already in the correct position. So I'm done. That one was easy. Okay, inserting 35 now. I can see that I'm going to be swapping the 35 all the way down to this position right here, where the 38 is. So I'm just going to do that in double speed, 96, 92, 92, 67, 55, 53, 38, and there goes to 35. Right, 2 more to go. So 43 is going to get swapped all the way down here to where the 53 is. Everything else is going to move up. 6, 92, 92, 67, 5, 53. And then I was inserting 43 right line. And one more number to insert. We're going to insert the 60. Notice that unlike the other two sorts, on this one, when we get to the point where there's only one item left that hasn't been processed, we can't stop. We still have to insert it into the correct position in the list, right? So 60 is going to get swapped down to here where the 67 is. So I'm going to move the 96 over, move the 92 over, move the 90 over, move the 82 over, move the 67 over, and there goes the 60. Okay. Any questions about the process there? Did I have to do an additional pass through the array compared to the other two sorts we've looked at? But I'm going to answer that because I realize it's kind of a trick question. The answer is no. I'm still only doing n-1 passes. The difference is that with the other two sorts, I kind of got to skip the last pass, right? I didn't have to sort that last number. But on this one, the first pass is free, right? There's no pass to get the first number processed. So n-1 passes. Each time through the array, we're going to be doing roughly n divided by 2 comparisons, right? We're going to just call it n. We're going to say n comparisons on each pass, n passes. So once again, we're kind of stuck at n squared, right? Any questions about how I got n squared? It's almost exactly the same conversation we had with the other two sorts, right? And again, just looking at this visually, it looks like a square. And that's sort of a hint about what the big O is going to turn out to be. Okay. Let's look at the code. Here is insertion sort. Shorter, right? Less code than the other two. Here's our outer loop. Notice that we're still doing num items -1 iterations, but instead of 0 to num items -1, we're doing 1 to num items. So I is going to represent the index of the first element, well, of the element that we are currently on this pass adding to the new list, right? Or another way of putting that is the index, I is always going to be the index of the first element of the part of the array that has not yet been sorted. So inside the loop, try that again. Inside the loop, we set j equal to that first item that hasn't been sorted yet. And then we go backwards so now that is the index of the number we're inserting, right? And so now we go backwards through the array until we get to a point where our number is, I said too many negatives there. As long as the number we're inserting is smaller than the number that we're looking at, or in other words, the number to its left, we're gonna swap and move to the left, okay? And then here's that extra condition that makes it stop when we reach index 0, if what we're inserting turns out to be the smallest item in the new list. So if that, I mean, I know that throwing code up on the screen and, you know, having 1 minute to stare at it and understand it is not always easy. So if that's not crystal clear, I hope that you will have a chance to just kind of stare at this for a few minutes sometime and convince yourself that it's working, or convince yourself why it's working. So just for fun, let's try it out. I need to uncomment that part of main. Can't tell if I saved it. Yeah, I did. So what are we at? 25,000? Yeah, I'll just do it, but I kind of wanted to do 50. So bubble 2.2, bubble 2 is 2.2 or so. Selection is this weird 0.7 seconds. Insertion, about a second, right? So twice as fast as bubble sort. And this turns out to actually be pretty accurate. Insertion sort does tend to be faster than bubble sort. Just for fun, I can't resist. I want to do 50,000. So 9.1. 9.3. 3 seconds. 4.3 seconds. Okay, and it should be times 4, right? And so we went from 1.03 seconds. So it's a little bit longer than times 4, but you know that's to be expected just because it depends on what the numbers are. Okay, so that's a good question. We were sort of attempting to improve our bubble sort, right? But it turned out that we ended up with something slower. And I think I mentioned, basically that turns out to be because we've got, every time through the loop, we're doing something extra, right? Every time we do a swap, we're having to do an assignment that we didn't have to do before. And then this isn't as much of a big issue, but for each pass through the array, we have to do an extra comparison and an extra assignment. But the really big deal is this, right? Because this happens every time we do a swap. So that slows bubble sort 2 down enough so that it actually makes it slower. And the other thing is that bubble sort 2 only helps if we end up with some sorted items at the end. And what's the probability of that? Actually pretty low, right? I mean, there's a 50% chance that we don't have to, the last two items, well, I guess it's probably higher than 50% because we've already been bubbling things around, but I'd have to think about that. I'm not sure. But anyway, the chances that we have a significant number of items that are already sorted when we get down to that point in the array is pretty low. So, well, it's hard to tell. It looks like we're pretty consistently getting slightly slower times from bubble sort 2. But maybe the check should start happening after 50%. Yeah, that's not a bad idea. But honestly, if you're really that concerned about gaining a couple of milliseconds, probably should just use a different sort and forget about bubble sort. Yeah, and then the other thing that I guess I want to point out is that you know, kind of playing around with the edges a little bit to gain, you know, a billion for the second here or there is not really what we're focused on here. What's going to happen is, I mean, so basically the bottom line is none of these sorts that we've talked about so far are even close to being acceptable if the array is big, right? We got to find a faster way. If, you know, imagine if we had 1 million items in the array. It would take days probably, right? So prohibitively, so again, let me say it this way. The natural solution to the problem turns out to be prohibitively inefficient. Just isn't going to work for us unless we've just got, you know, maybe a few hundred elements in the array, or even a few thousand, I guess. But once we get up to the tens of thousands, it's not acceptable. So that's a good segue into talking about our next sorting algorithm. I guess we'll try to cover one more. We'll see how it goes. Okay, so the next sorting algorithm we're going to talk about is merge sort. I capitalized all the other ones, didn't I? I guess I should be consistent. Okay. Here's the strategy with merge sort. And I have to admit that I have not figured out a really great way to do this one on the spreadsheet, but I'm going to give it another try. I have a couple ideas, but I think I'm going to have to make my cells a little bit narrower. I'm kind of aiming, well, let's, all right, we'll try this. All right, so this one's kind of fun. Here's what we're going to do. The strategy is, first of all, the strategy is, let's put the numbers in the middle. And then cut, not copy. And I'm going to put boxes in all of these so we can see that it is an array. Okay, here's the strategy. we are going to split the list in half, and we are going to sort each half. Then guess how we, let me try that again. Guess how we are going to sort each half. We're going to do the same thing. We're going to split each half in half and sort those lists. So let's give that a try. So what I need to do is I need, let's see, this is 12, is that right? 2, 4, 6, 8, 10, 12. So I'm going to need 6 of them to go on one side. No. And I'm going to need 6 of them to go the other way. Okay, and I'm going to use some arrows or actually here so we can keep track of where things came from. Okay, so we split the list in half. Now we're going to do the same thing. We're going to split this list in half. So I'm going to take the first 3 and over here, second 3, and over here, first 3, and over here, second 3, and over here, and arrows.
It looks like you've pasted the wrong thing in the last 2.
Oh, thank you. You are correct about that. You keep splitting until the number of items split is 1. All right, I'm gonna have to fix this. Okay, now I'm gonna split these lists. So I'm gonna end up with, I think this is the farthest I go, so I might as well go all the way to the edge. There, and there. There. And there. Oops. Copying skills have something to be desired, I guess. In an ideal world, these would all be nice and symmetric beneath each tree, but I'm doing the best I can here. Let's bring this here. Ah, yeah. What? Okay. And then I'm gonna,
No, the last one I think is bogus.
still wrong. My Command C is not working very well for some reason. How's that? All right. I think I'm getting a little bit faster with the arrows. Wait, what did I do? Oh no. Hold on a sec. I can use the same arrows if I just space this out the same. So let's insert arrow. And then I can use this arrow. And I can also use the same arrow. Here. And here. And here. And this one. Here. They're going to cross a little bit, but that's okay. And here. Sorry, that's probably a little bit confusing, but I'm going to go with it, I think. Actually, what happens if I just move this over? That's better. Or not. All right, sorry guys, I'm going to play here for a minute. I'm going to move. Oh no. I can move this guy over one. So of course now this one's a little bit off, but sorry, I can't resist. No, that's not what I need to do. I can move this guy. This guy. All right. I'm happier now. All right, the bad news is we're still not done splitting, right? We've got to split these guys. We go all the way. I mean, so, you know, technically in the algorithm, you could set it up so that when you get down to size 2, you just compare them and swap if they're in the wrong order. But I'm going to just be masochistic here and go all the way. So we're going to split this into 2. What did I just do? It's a little complicated, yeah, but the good news is that it's really efficient. That happens sometimes with algorithms, right? You want something efficient, gets a little complicated. The fact that I'm using Excel probably makes it a lot more complicated too. Okay, I'm not going to worry about whether the arrows work or not. Hey. Oh boy. Wow. Okay. This is all going to be worth it, I promise. Um, I don't know why I didn't just do that before. Oh boy. All right, this is my first time doing this. Next semester, hopefully none of you will be around, right? But if you are, this is going to go so fast you're not even going to believe it. Okay. Okay, so what we've done here is we have split everything up so that the size of every list, we know every list is sorted because it is of size 1, right? Now basically we just start putting things back together again. So we put the 55 and the 92 together. We put the 90 and the 38 together, but when we put them together, we're going to be putting them in the right order. Now, I'm guessing what's going through your mind. What you're probably thinking, shoot, you're probably thinking, why didn't we just do that without splitting them? The point is, you're right with this little baby example. That probably would have been more efficient, but when we get to bigger lists, this is going to be a pretty big win. So combining the 53 and the 96 gives us that. Combining the 43 and the 60, whoops, gives us this. Now, you watched me create these. I just want to point out that I created these by copying and pasting from up here, but that's not what's actually happening, right? What's actually happening here is I've got these two lists and I am merging them into a single list and getting this as a result. And in this particular case, they were in the wrong order. So what happens is you split it into two lists and then you merge those two lists back into one list and it's sorted. All right, so more fun with arrows. Okay. Now we're going to be combining to get back up to our list of size 3. When I say combining, I should just use the word merge because that's what we're doing. That's where the sort gets its name, right? We're merging our lists back together again into sorted lists. And so when you see the code, you'll see a little bit more about why this is a big win. But so don't watch. I'm going to copy from here, even though that's not what's going on. And put those in the right order. Okay, and that came from here and here. Okay, and then 67, 38, 90. It's going to be here. Oy. Try that again. Here. And here. And then down here, we're going to have the 15 combined with the 5396. Coincidentally, already in the correct order. And then the 35 and the 4360 combined into one list. Okay, now we have to combine these two lists into one big one. So so let me just make an observation here now. It's actually not that complicated. The only thing that should be hurting is my fingers from doing all this stuff on the keyboard. When I am combining, I'm merging these two lists, that turns out to be a pretty efficient process because I don't have to do a lot of swapping around and stuff. I just take the smallest number from each list. So let's go through this in a little bit of detail, actually. The process of combining these two lists is I'm going to keep an index into the right list and an index into the left list. I'm gonna, I'm just gonna put a mark down here to indicate where the index is pointing currently. Okay, I'm gonna take the smallest of those two. Let me actually clear out these contents. I'm gonna take the smallest of those two and put it here in the first element of the new array. And then I'm gonna move this up. Okay, now I compare the 55 and the 67. The 55 is smaller, so it goes next. And I move this up. Compare the 82 and the 67. The 67 is smaller, so it goes there. And I move this up. Compare 82 and 90. 82 is smaller, so I put the 82 there. And I move this up. Compare the 92 and the 90. 90 is smaller, so the 90 goes there. And now I can't move this up. And so that tells me that whatever's left over here in this list just gets copied down. Okay. And then same thing here. I'm going to end up with a list with 6 items in it. So I'm just going to use this list and then delete the contents. Okay, so I'm going to have pointer here, not a pointer, but it's an index that I kind of think of as pointing into the array. Smallest between 15 and 35 is 15, so the 15 goes there. And I move this up. 53 and 35, 35 is smaller, so it goes next. And I move this index up. 53 and 43, 43 is smaller, so it goes next. And I move this index up. 53 and 60, 53 is smaller, so I put the 53 there. And move this index up. 96 and 60, 60 is smaller, so it goes in. And I can't move the index up, so that means I copy the rest of the other list in. Okay, so that's our process of merging lists together. I realize we're going over a little bit. Almost done. Hope that's okay. And we'll talk about Big O and look at the code next week. But okay, let's get a list. Let's merge these 2 lists together now. Okay, so I'm going to need 12 items. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's. Okay, so there's our empty array. Going to have a pointer here. No, I'm sorry, not a pointer, an index that points there. Between 38 and 15, 15 is smaller. Move this up. Between 35 and 38, 35 is smaller. Move this up. Between 43 and 38, 38 is smaller. Move this up. Between 55 and 43, 43 is smaller. Move this up. Between 53 and 55, 53 is smaller. Move this up. Between 55 and 60, 55 is smaller. Move this up. Between 60 and 67, 60 is smaller. Move this up. Between 67 and 96, 67 is smaller. Move this up. Between 82 and 96, 82 is smaller. Move this up. Between 90 and 96, 90 is smaller. Move this up. Between 92 and 96, 92 is smaller. Can't move this up, so copy the remaining items in the other array. Okay. Let me ask, no, I guess I better not. Let's just, I will wrap this up for us and we will talk more next time. But we need to connect these all up with arrows, right? So I only need a few more arrows and I will be done. Of course, I made it so you can't see the whole picture at once. Okay. I'm gonna unzoom this just a little bit. A little bit more. So we can see the whole picture. So there you go. We split the list into half until we get down to size 1, and then we merge them back together, creating sorted lists each step of the way as we go. You guys want me to talk for another 3 minutes about Big O, or do you want me to just do it on Tuesday? Any votes? Do it now. Okay, I will do it now. If you can't stick around, you can watch the recording. So these first passes to get from the list of length 12 to the lists of length 1, each takes just one step, right? It's not a one or two, it's a constant operation. It doesn't take longer to do to split a list into 2 if the list is really big. So these steps of splitting basically are trivial. We're not even going to consider them in our calculation because they are, what's the word? Overwhelmed by the amount of time that it takes to merge everything back together again. Okay, so the question is, each of these rows, okay, so I've got a row here, merging lists back together again, and I've got a row here, merging the lists of 1 and 2 back into lists of 3, and I've got a row here, merging the lists of 3 back into lists of 6, and I've got a row at the bottom, merging the lists of 6 into a list of 12. How many comparisons does each of those levels require? For example, the very last one. I had to look at each, I think it might be easier in this case to think about it in terms of how many elements I have to look at, right? I have to look at each element in this list at least once, maybe twice, maybe twice, but at least once or twice, in order to merge these 2 lists back into 1. So what's the big O of merging these 2 lists back into 1 big list? I've got n items in my array. I'm looking at each of them one time. So the process of getting from this level to this level is n. That's correct. Same thing here, right? There's more lists, but I'm still looking at each element one time. So the process of getting from this level to this level is n. Same here. The process of getting from this level to this level is n. Okay? So each getting from one level to the next costs n. Next question is, how many of those levels are there? How many times do we have to combine? So for example, in this case, we had to combine 1, 2, 3, 4 times, right? So n was 12, but we had to combine 4 times. If n was 24, how many times would we have to combine? Well, with n being 12, we had to combine 4 times, right? If n is 24, we just have to combine 1 more time, right? If I had 24 items, I would have ended up with 2 lists of 12 here, right? And then I would have just combined those 2 lists of 12. So it would have been 5 levels instead of 4. I'm going to call them passes, 5 passes instead of 4, right? And then if I had 48 items, I would just have to do that twice. So it would be, well, let's look at it this way. If I have, instead of using 12, I'm going to use 8. If I've got 8 items, how many times am I going to have to combine them? I combine the 1s into 2s, I combine the 2s into 4s, and then I combine the 4s into 8s. So that's 3 times, right? Everyone with me on that? Yes. 8 is 3, 12 is 4, but let's not use 12. Let's use 16. If there's 16, then I do what I just did with the 8, right? Combine the 1s to get 2s, combine the 2s to get 4s, combine the 4s to get 8s, and then just combine the 8s to get 16. So I just have to go one more. Yeah. Right? What about 32? If I've got 32 elements, how many times am I going to have to combine them? Right, just one more time. This is super, super important right here. I hope, if this isn't making sense, watch it over and over again until it makes sense. Okay, so can you tell me what kind of a function that is? How do I get from n, like if I was in algebra and my instructor asked me, okay, what's f of n? What is that function? Not sure? We've actually had this conversation before. Okay, so let me ask you this then. What if I was going the other way? How do I get from this column to this column? Or here's another hint. What do all of these numbers have in common? They are all right. Right, Mark. So the way to get from this column from the right column to the left column would be 2 to the, we'll call it y, right? If this was x and y. The way to get from y to x is 2 to the y equals x, right? So exactly, going the opposite direction is just the opposite of exponent, so it's log. So to summarize, the number of times that we have to merge lists together is log n. Okay, it's log base 2 of n, but we don't care about the base 2, we just say it's log n. So we've got log n times that we merge. Each level of merging costs n. So what's the total running time in big O of merge sort? Yes, that's a good observation, but we're not quite done figuring out what the big O is for merge sort, right? So we figured out that, we didn't figure out that merge sort is log n. We figured out that the number of times we have to merge is log n. Just like, in bubble sort, the number of times we had to go through the array was n, right? But that didn't make big O, that didn't make bubble sort big O of n, it made bubble sort big O of n squared. Right, because each time we merge, we're doing something that's big O of n. So the bottom line is merge sort is big O in log n. Okay? All right. if I was going to keep going, which I'm not, but if I was going to keep going, what I would do is I would say, okay, let's plug in some numbers here. You know, how big is of a difference is n squared versus n log n? And you will probably not be surprised to find out that it's a pretty huge difference. So merge sort is a pretty huge win over the quadratic sorts that we've been looking at so far. All right, got to stop there. I'll see you guys on Tuesday.
Thanks, Dave.
All right.